Okay, philosophers, so you have learned 8 implication rules that help you do proofs or derivations. And these implication rules are argument forms. We're going to add to the implication rules 10 more rules. And these rules are called replacement rules. And we're going to break them down into 2 sets of 5 each. So 8E discusses replacement rules number 1, the first set, and the replacement rules number 2 is in 8F. And here's the names of them and their abbreviations, and I'll briefly talk through each of them. So first of all, the difference between replacement rules and implication rules. Your implication rules took multiple premises, like premise, at least one premise, or usually 2 premises, and a conclusion. Now, and you could, with implication rules, you couldn't use an implication on just part of a line. It had to apply to the whole line, right? Replacement rules are different. They are pairs of logically equivalent expressions, and you can replace one of the pair with the other, with its correlative, anywhere they occur, even if it's just part of a line, which is really powerful and cool. And we use a new symbol, it's like double colons, to express the relationship between these logically equivalent statements. So let's start with the first set of 5. Okay. And we're going to start with De Morgan, which is named after a logician in the 19th century. I love this rule. I hope you will come to love it too. Memorize what's in the box. Basically, it says, look, the negation of a conjunction is logically equivalent to a disjunction of the negation of both of those conjuncts. Is that helpful? Is that really super clear? All right, let's look at what's in the box here. It says not P and Q is logically equivalent to not P or not Q. So think about it this way. Let me say it a different way. If it's not the case that you can have both chocolate and vanilla ice cream, then either you're not going to have chocolate or you're not going to have vanilla. One or the other is false, right? If they're not both true, then at least one is false. That's the idea. And then, another application of De Morgan's, it says, look, if it's not true that either P or Q is true, then that means that they're both false. They've both got to be false. Like if it's not true either that you can have chocolate or that you can have vanilla, that means that you can't have chocolate and you can't have vanilla. Okay, so here's some valid applications of De Morgan's. So if you've got line 4 here, which says either not A or not B, maybe you got that by addition, doesn't matter how you got it. You can immediately infer just from line 4, the logically equivalent statement, that it is not the case that both A and B are true by De Morgan's. All right, here's a misapplication of De Morgan's. You can't go from 1 to 2. 1 says it's not the case that both A and B are true. 2 says it's not the case that A and it's not the case that B. No, friends, that is not it. If you are negating a conjunction, then what you should have is a disjunction as a conclusion, right? You should have, if it's not the case that you can have chocolate and vanilla, then either you can't have chocolate or you can't have vanilla, but it's not necessarily the case that both of these are false. Could be, but it's not necessarily. This, in other words, the dot on line 2 should be a wedge. All right, and then over here, the next one with the C's and the D's. Line 1 says either not C or not D. And then the conclusion is it's not the case that either C or D. Well, that's not, look, the first one says that at least either C or D is false, right? Either C is false or D is false. Line 2 says they're both false. Neither is true. Wrong. So on line 2, the wedge should be a dot. All right, that's De Morgan's. Memorize it. It's great. Second, double negation. This one's easy. P is logically equivalent to not P. So if it's not the case that P is false, if it's false that P is false, then P is true. It's like double negation. It's double negation. Like in math, you know, two negatives are positive. So yeah, that's how it works. Here's how to screw it up. Line 1, Q or R. Line 2, it's not the case that either not Q or not R. Now here's the key screw up that was made here. If you want to apply double negation to line 1 and to that whole disjunction, then put parentheses around Q or R and say negation, negation, parentheses, Q or R, close parentheses. But you can't, like, you know, spread out the two negations across parentheses like this. That doesn't work. 3, commutation. This one's, I like this one. It's just like a switch of position. So I think of it like, you know, you're commuting. When you commute, you change your position, and that's what happens here. So P or Q is logically equivalent to Q or P. So let's just swap their positions. They commute back and forth in the different positions. Isn't that clever? It's kind of cute. And the same thing will work with a conjunction, a dot sign. P and Q is equivalent to Q and P. Same difference. How they screw it up here. Oh, you can't do commutation, friends, with a horseshoe, because the different sides of a horseshoe is like two totally different worlds. I mean, don't do that. You can't just swap those consequence and antecedents back and forth. Commutation only works with a disjunction or a conjunction, with a wedge or a dot. Next, association. This has to do with, like, who do these statements really want to associate with? Who do they want to be next to? All right, so and really it just has to do with, if you have a series of two wedges or a series of two dots in a row, then there's going to be parentheses, but you can move those parentheses around. So if you got P or Q or R, then you can move the parentheses so it's P or Q or R. That's logically equivalent. And the same if you got dots, right? Now, so here, how did they screw this up? Here, what's the misapplication? Well, here's the problem. On line 1, you don't have a series of like wedge and wedge. You got dot then wedge. Friends, you can't just start sliding parentheses around if you got a dot and then a wedge, or a wedge and then a dot. Nope, doesn't work. It only works if you got wedge, wedge, or dot, dot. If you got wedge, dot, then you need to think about doing distribution, but that's a totally different rule. Here it is. Here's that. Okay, so if you got a series of like dot then wedge, or wedge then dot, you can do distribution. But here's how this works. It's quite different. If you've got P and Q or R, that's logically equivalent to saying that either P and Q are both true, or P and R are both true. Because P is definitely true. It's just like which partner he's got. It's one of those two. Or if you've got P or Q and R, that's logically equivalent to P or Q and P or R. It's P or something. Now here's the thing that's helpful to me. When you move back and forth across those double colons, when you apply distribution, the main operator is going to change. So it goes from the main operator was a dot here on this top line, and then it's a wedge over on the other side. So if it starts as a wedge, it's going to become a dot, the main operator. And if it starts as a wedge, yeah, it starts as a dot, then it's going to become a wedge. And the other operator is going to go from being outside parentheses to being inside parentheses. That helps me. Maybe it just confuses you. What did they do wrong here in this misapplication? Let's see, we had M and N, or M and P. And it went to M and N and P. What's the mess up here? Well, all of a sudden we've got a line of like dot, dot. Distribution involves dot and wedge. So this N and P, it should be N or P is what it should be. And then here we've got P and if Q then R. You can't, friends, you can't do distribution with a horseshoe. When it's got it, no, doesn't work. Can't distribute over a horseshoe. All right, those are our lines, our rules from 8E. Now, okay, so they give you a bunch of tactics to use with these replacement rules. I mean, these are helpful. I find them like kind of, it's a lot. I mean, if you think through each one of them, they can be helpful to you. I've never sat and like memorized all 15 tactics. I learned the rules really well, and then I've got a method I use to employ them. But I mean, this is all true. I'm just not going to bother with it. If it helps you, great, go for it. Okay, so but we'll look at an exercise here. If we were to apply De Morgan's to line 1, what would we get? And what we've got here is the negation of a conjunction. Don't get distracted by this horseshoe, because this whole conditional statement is just one conjunct within this conjunction, which is getting negated. So this says it's not the case that both these conjuncts are true. So at least one of them is false, right? So either it's not the case that if S then R, or it's not the case that B. That's how you apply De Morgan's. And then here's kind of a proof one. Now, I'm going to give you a method in another video about how to solve proofs with replacement rules. And so I'm not going to get into that now. But if you were to just look at the premises for this, let's check this out. All right, I'm supposed to get to the conclusion M. And M is in premise 1. And in premise 1, it's in the two consequence of two conditional statements. Premise 1 is a pair of conditional statements, and each consequent is a conjunction. And one of the conjuncts in each of those is an M. All right, so that's somehow my target. And then, interestingly, coincidentally, I happen to have the second premise P, which is a disjunction. And each of the disjuncts is the antecedent for one of the conditional statements that I have in premise 1. Friends, if you know your rules, there is like a special Karate Kid crane kick logical move that you should be trying to make right now. What is it? Oh, that's right. It's the constructive dilemma. Wow. Okay, so if you apply constructive dilemma, here's what that's going to give you. It's just going to give you the consequence of those two conditionals, which has the M's in it. So we got L and M, or M and Q. How am I going to get the M out of there, out of either one of those? It's like I want to get the M by itself. Do you know a rule that will help get the M by itself? Well, something jumping out at you? The rule that's coming to mind for me is distribution. But I can't do distribution yet. You might think, Sasha, why not? It's right there. Because you got to get the order exactly right. If you're going to do distribution on this, then the M has got to come first in both of those conjunctions. But it's not first in both conjunctions. So we need to like change the position of the M in one of the conjunctions. What rule do you know that will let you change positions of the M? It will help it to commute to a different place. That's right, it's commutation. Voila. So now we've got M and L, or M and Q. Now you can apply your distribution rule. Isolate the M. There it is, M and L or Q. And now you could definitely get the M. Bring it home with an old, friendly, easy, simple implication rule. What is it? Simplification. Boom. There we are. Now, we work this in like the reverse order that I taught you to think about it, right? Because I taught you to think backwards from the conclusion, and we were kind of like working our way forward, seeing what rules we could apply in many ways. So I'm going to give you a method in my other video where you can help you think backwards using replacement rules, but that's for another time. Let's take a much deserved break right now.